For the last talk, which is called The Effect of Third-Party Implementations on Reproducibility by Bala Shidasi and Adam Zapp. This presents the results of a reproducibility study comparing several third-party implementations of the same algorithm to the original implementation by Balash, where without spoiling too much, they found some surprisingly big differences.
Thank you. Almost there. It's just need to. Okay, now we have the slides. So thank you for the introduction. So I will be talking about the effect of third-party implementations on reproducibility. Even though our interpretations might be different of it, as scientists we can all agree that reproducibility is very important for us because it is the core of the scientific process. And even if your interpretation of it is very narrow, so you are only interested in reproducing papers and results in your own proprietary A/B test system, if evaluation setups in RecSys papers are uninformative, then it also hinders your work, because you will have no idea, based on the evaluation section of the paper, whether you should try it or not, whether it would be good for you or not. And if you have looked at some of the papers coming out in the last 5 years, then you can see that the situation is not good. So the results of the baselines, the performance of the baselines are all over the place. And evaluation setups often don't really make sense. So I think that it's important to talk about reproducibility, even if you are from the industry like I am. So in this research community, when we talk about reproducibility, we often talk about the reproducibility of offline evaluation setups. And we know that this is an imperfect proxy of online performance due to the interactive nature of recommender systems. But the problem with online A/B tests that they are not reproducible by independent research groups due to the proprietary nature of the production recommender systems. And we also know that the online A/B test is not the end of be all. It's basically just another step in the chain of approximation that we have to basically measure how the recommender fulfills its goal. Both online and offline evaluation really depends on the setup that we use for them. And these are not trivial to do right. And if you are interested in some of the flows that are in offline evaluation setups that you could also see on the workshop days, and we'll probably see throughout the conference in some of the papers, then come visit our poster tomorrow. But we are not here to talk about evaluation setups. We are also not here to talk about hyperparameter optimization, which is also another important step to measure the performance of algorithms correctly. We are here to talk about a quite neglected aspect of tests, which is implementation and what implementation of the algorithms we use. So why do people re-implement algorithms? There is the standard one, the personal re-implementation. Basically, if you want to use a baseline and the code is not available, or it is available but you want to do something different with it, you do some personal re-implementation of the algorithm. You also might want to do a production re-implementation if you plan to use it in a live system, because then your algorithm needs to adhere to efficiency and other requirements. Why these re-implementations are important and their quality is very important, these are the ones that we cannot really see as a community because these are private ones. What we can see are the public implementation, which is usually a re-implementation in different programming language to increase accessibility, or maybe the code is not available, so someone made an implementation based on the paper. And the final one is the reimplementations in benchmarking frameworks, where the goal is to use the algorithm with a unified evaluator and use every baseline with a unified evaluator. And the question really is, are the reimplementations correct representations of the original or not? So we couldn't really check every reimplementation of every algorithm out there. So we choose a single one, GRU for Rec or GRU for Rec. This is a seminal work of its field, session-based recommendations and sequential recommendations. This was basically one of the algorithms that started with field, so it's often used as a baseline. And as we saw in the opening, the sequential recommendations gained quite a popularity throughout the years. Another reason we chose this algorithm because there is an official public implementation available, and it has been available since early 2016. So there is some basis for the reimplementations to work on. You don't have to reimplement it based on the paper alone. The algorithm is also very simple, so it should be trivial to reimplement it, but it also has some adaptations that adapted the GRU to the recommender systems domain. And the final reason is because it's implemented in Tiano. Those of you that don't really know Tiano, it's an older deep learning framework that has been discontinued. So there is also an additional motivation for re-implementing this algorithm in other more popular frameworks. We checked 6 re-implementations of this algorithm, 2 in PyTorch, 2 in TensorFlow, and 2 in benchmarking frameworks. These 2 benchmarking frameworks are the Microsoft Recommenders collection, which is probably the largest recommender algorithms collections out there, and also a more recent benchmarking framework, RecPack. And we saw that both of these frameworks are recommended by the organizers of RecSys to encourage reproducibility of the work. We also know of 2 other implementations, but we haven't checked them in the paper. We checked them outside, and I won't really talk about them in this presentation. So we broke this down into 5 questions. So the first question is, do they implement the same algorithm as the original? As you might guess, this is quite an important question to ask. And if the answer is no, then what we are really talking about? There are a lot of boxes on this slide, but the architecture GRU for Rec is very simple. Basically, you embed some items, run them through a GRU layer, then you embed target items and negative samples, take the dot product, you have scores, and now you can compute the loss function. 5 of the 6 candidates could do this architecture, but we were quite surprised that the one in the Microsoft Recommenders could not implement this architecture. They did something different. First of all, they work on sequences, but this is not really a big deal. GRU for Rec also has a version where it works on sequences, not just one-step transitions, but it's not really useful for session-based recommendations, so it's not out there publicly. But the main problem with this Microsoft Recommenders one is once it has the session representation, it clones it as many times as there are negative samples for a single target item in the mini-batch, and then pairs up the target and the negative samples with the session states and runs it through a feed-forward network. And the problem, besides this being completely different from the original, so you cannot really call it a re-implementation, is also that this is a severe scalability issue for the algorithm. So the number of negative samples is limited both during training and both during evaluation, and it is not able to rank all items during inference. So I could say it's completely flawed and GRU for Rec in name only. So for the rest of the talk, we will only talk about the other 5 who could manage to do the architecture right. The next question we wanted to ask is, do they have all of the same features as the original? Remember that the GRU for Rec is GRU adapted for the recommendation problem, and it has 8 distinctive features to do so. It also has a lot of hyperparameters. And as you can see in the table, none of the re-implementations managed to get all of the features. Maybe Torch GRU for Rec comes to closest with only missing the shared embedding feature. But it also misses some of the hyperparameters, which is not listed in the table, but every reimplementation misses at least one or two hyperparameters that we have. So, okay, these are just the features, but what they have, is this correct? So if you take the features they have, are those implemented correctly? This is the third question that we wanted to ask, and for this, we divided the errors into 5 categories. So basic errors are mostly like syntax errors, typos, anything that someone who wants to use these tools would fix immediately. Then we also have inference errors that only affect the evaluator that are bundled together with these algorithms. The next one is minor errors that are easy to notice and easy to fix and will be likely fixed by an experienced user. You can think about things like hard-coded hyperparameters, or the algorithm doesn't converge because the accumulator has large initial values or things like that. Then there are more severe category, the major errors, where the errors are hard to notice or hard to fix. But these may be fixed by a very thorough user who looks over all of the code and fixes everything he finds. You can think about stuff like the hidden states are reset incorrectly, or the sampling and the softmax are in reverse order, or anything like that. And then there are the core errors, where it would be easier for you to re-implement the whole thing from scratch than fix these errors. As you can see, all of the re-implementations have multiple errors from multiple categories. So, okay, we don't have all of the features, and there are some errors in the code, but does it really matter? Can they bring the same performance even though the flaws they have? So for this, what we did is that we gradually improved the re-implementations. So for the out-of-the-box, we fixed the basic errors, the inference fix, we fixed the errors in the evaluator code, minor fix minor errors, major fix major errors. You get how it works. We also dumbed down the official version to match the feature set that the re-implementation has. In this way, we can define different errors, like the degradation of performance loss due to errors, degradation due to missing features, total degradation, and so on. And what is really frightening is that when we ran experiments on 5 public session-based datasets using the next item prediction task, we found that the median performance loss for the best performing algorithm is already 7.5%. And for the worst performing algorithm is almost 90%. And this is just the median performance loss. If you look at the worst case scenario, for the very popular PyTorch and TensorFlow reimplementation, you can see it's more than 90%, it gets more than 90% worse performance than the original, which is a lot. So if you use them as a baseline, you don't get any informative results on the performance of this baseline. But also the other algorithms are not performing well. So even Torch Group 4Rec, which was the best one, has a worst case performance loss of 27%. But we wanted to ask one final question. How do they fare with respect to training time? And as you can see, the situation is also terrible here. You can barely see the running time of the original one on these graphs. This is mainly due to the RecPack and the Keras Group 4Rec one not being scalable due to the lack of sampling. But if you ignore those ones and only look at the other ones where there is sampling, you can also see that, for example, on one of the graphs, the training time is like 20 times more than that of the original. And some of this is due to the framework used and how those frameworks work. I won't go into detail, but as you can see, for reference, we put out how our re-implementations in PyTorch and TensorFlow are work with respect to running time. So to summarize, what does all of this mean? So from 6 very popular re-implementation of a popular baseline, one couldn't be called GRU4Rec at all because it implements a different architecture and it's deeply flawed. The other versions miss at least one of the features of the original. They have several serious implementation errors, and some of them scale very poorly. So The potential impact of this is that a lot of research from the last 5 to 7 years, and especially since Theano has been discontinued, so for like 3-4 years, a lot of research didn't get the right baseline results and might be not even state-of-the-art. It's hard to tell because usually papers don't mention which implementations they use. And GRU4Rec is probably not the only algorithm affected by this. So when there is a paper and when there is a public implementation and the re-implementations are still not working, you can guess how it translates to more complex algorithms or for algorithms when there is no official code or things like that. And this also brings up a lot of interesting discussion topics, which I won't go into detail now, but basically, can we trust the tools that we are using, the baselines others implemented, or our own baselines? How is this responsibility shared? How can we correct the works that are affected? What I want to focus instead in the last minute is, what can you do about this? So if you are a researcher and you use the flowed version, just try to rerun the experiment with the official code and extend your work with the results. Not the paper, you cannot do that, but maybe put it on a website or something like that. If you just want to help, try to check other re-implementations of other popular baselines. If you are an author, always try to say which re-implementation you used, and also use the official code if possible. If you re-implement an algorithm, and this is the most important one, try to validate your algorithm before you release it. Compare it to the original based on different data sets using different hyperparameter setups. Compare the recommendation list. Compare if you have every feature and setting. Compare training times. Whatever we did in this work should be enough. And if you are a maintainer of a benchmarking framework, you should do the same, but you should also validate every implementation submitted by the contributors. And finally, I just want to say that we also want to help in this situation, so we did what we could. We released an official implementation of GRU4Rec both in PyTorch and TensorFlow, so if you are interested, check those out. You can also read the paper and check out the project website. Thank you.
Thank you for your presentation, Balázs. There are 3 questions on Slido, and I'll come over so you can also read them. Maybe we should start with this one. I'll read it while you read it. How should we choose the implementation in industry that we're using in industry? Does the only thing we can do is compare all implementations?
So what I would say is that if you can use the official code, if you cannot, for some kind of reason like efficiency or scalability, then you are probably the best thing to do is to re-implement your own baseline that adheres to all of the constraints that you have. You just need to validate it against the official implementation so you can get the same results.
Thanks. I'll ask one of my own questions as well. You were the original author of this, or creator of this algorithm, right? How much did that help you in detecting all of these different errors? Because if someone else were to do the same thing, right, would they have a much harder time of it?
Well, the trick was that I didn't do the conversion myself, so the codes were overviewed by my colleague, Adam. So I think that others who are thorough can also get these results fairly easy. So there were some problems during the experiments, but it was mostly related to how do we fix those errors, not really to noticing the errors.
Okay. About errors, there's also a question on Slido. This one. How did you consolidate the errors of re-implementations?
Okay, so we put them into these categories that I discussed, and we decided that some of them cannot be fixed because then we would need to rewrite like 50% of the code, so it's not feasible, and the researchers who use these codes wouldn't really do that. As for the other ones, how do we put them into categories? It was somewhat subjective in how much time and effort it took us to notice or fix the errors. And basically, we then just went through with it and tried to make it work similarly to the original by fixing those errors.
There's 3 more questions for you here, right? And I encourage all the presenters actually to go on Slido and answer their questions. There's a few more that came in for the Google DeepMind people. We have time for one more. These are both really interesting. I'll go with this one. You mentioned that other people's work is very flawed. A strong claim. I'm very curious how the authors react when you approach them asking to fix their bugs.
Well, for the reason of this work, we did not approach the authors to fix these bugs. This is more of a call to action, well, not just for authors of reimplementations of Groove4Rec to fix their work, but also to authors of other reimplementations to check their work against the original and fix the bugs. You are right in the sense that the next step, if we want to make things right, is to report these bugs to those who committed them. But for the reason of this work, this was not a crucial step.
Okay, thanks a lot. Let's thank the speaker again for his presentation. That is the end of this session. It is time for lunch now, and that is on your own, so it's not provided by the conference. And we meet again at 2. And remember that all the posters are also available during lunchtime, right? Thanks a lot for attending this session.